In this tutorial, I'm going to discuss the take-up inputs and outputs in Sidewinder. In the next tutorial, I'm going to get into the difference between the gravity and fixed and automatic take-up tension. But in this tutorial, we're going to focus just on all the inputs and the outputs and how Sidewinder calculates the take-up system and so on and so forth. So I've opened up the same tutorial that we've been working with, this decline-incline conveyor. Again, we just have a single drive with the take-up system at the head. And when I go ahead and run this conveyor, we can see that Sidewinder has selected a take-up tension of 62.3 kilonewtons. Now, essentially Sidewinder looks at two different things. There are two main requirements for the take-up tension. They are the belt sag requirement. In other words, what minimum tension do we require to maintain our minimum design sag level? And that's done for both steady state and for dynamic conditions. The other input is the tension ratio. In other words, how much take-up tension do we need to prevent the belt from slipping on the drive pulley, or if we've got a braking case, on the brake pulley. So the belt sag and the belt tension ratio are our two parameters, and for each of those we've got a steady state and a dynamic condition. Now if you're wondering what the basis of those are, you can go under the project information tab, and on our design criteria we've got them right here. So maximum allowable sag during steady state condition is 1%. For dynamic conditions and all our design level 2s, i.e. our non-common loading conditions and whatnot, we're allowing 3% sag. Our tension ratios are based off of our friction factor. Again, if you're not familiar with tension ratios, you might want to refer to the SEMA or DIN standards and review that. But essentially the tension ratio T1 divided by T2 is equal to E to the theta F, where theta is our wrap angle and F is our friction factor. For rubber lagging, the default is 0.28. For ceramic lagging, it's 0.35. And for dynamic conditions, we've got a multiplier of 115, 1.15, 115%, i.e. during steady state running, the coefficient of friction is 0.28. During starting and stopping, it would be 0.28 times 1.15, which is 0.322 for rubber, or 0.35 times 1.5, which is 0.4025. So these right here are what are specifying our take-up tension. Now, if we had entered a take-up tension, those would also be the criteria that would show us if there was any problems. These cells would highlight in red if we exceeded those criteria. Now, I also want to point out that the belt line, the take-up tension, when you're working with a conveyor file, the take-up tension, entering and knowing your take-up tension is crucial. I mean, the take-up tension, the take-up system is essentially the heart of your conveyor. So no different than we can leave, we could leave the belt width and belt speed and rating, and we can leave all these variables blank, but as you progress with the conveyor design and as you nail down your design, you want to add it, you want to start entering these variables so they aren't floating all over the place. And just like the take-up tension, you want to be able to eventually specify that and continue on with your design. So it's fine to leave Sidewinder, go ahead and make an initial guess, but the point is as you nail down the design, you should be, these values should start to fill in these values. So when we ran this, why did Sidewinder pick a take-up tension of 62.3 kilonewtons? Well, if we look at our different cases here, if we start with our empty case, and before I do that, I'll just jump to our loading page just so you see this. We've got an empty case, a fully loaded case, a case with just our inclines loaded and our flats under high friction, and we've got a decline case under low friction. That's just what I'm using for this example file. So when we look at our empty case, we can see that Sidewinder is selected, or it's showing us what the take-up requirement is for each of these conditions. In other words, under steady state running, to meet our sag requirement, the take-up tension needs to be at least 10.9 kilonewtons. Under empty conditions, when we're running, to prevent the belt from slipping on the drives, we need a take-up tension of 11.1. Now under dynamic conditions, starting, stopping, so on and so forth, the sag requirement is we require a take-up tension of 17.9. And for starting and stopping, in this case it would be starting, we need a take-up tension of 33.8 kilonewtons. Okay, so that's our empty case. If we go to our fully loaded case, we can see that, in the empty case, the starting tension ratio requirement, that's what was governing it. In other words, that required the highest take-up tension. When we go to the fully loaded case, now we can see that actually the bold one, which is the largest number of all of them, actually the determining criteria is just steady state running for belt sag. So in other words, to meet our 1% belt sag that we specified under steady state running here, we need a take-up tension of 45.4. Now, if we were less stringent, I mean, if we said, let's say we're going to allow 1.5% belt sag during steady state running, and I run the calculations, now we can see that that's actually dropped to 36.1 is all we needed because we've allowed more belt sag. In that case, now the tension ratio became the governing criteria. But I'm going to jump back just to show you that. I'm going to jump back to 1% where we had. So in that case it was 45.4. Again, Sidewinder has picked 62.3. So where did this come from? Well, if we continue to look at the rest of our cases, we can see that our incline high friction case actually required a take-up tension of 59.2. And our decline case required 50.5. So our biggest number actually was our incline high of 59.2. So why did Sidewinder pick 62.3? Well, it's essentially Sidewinder takes the largest. It looks at all your different load cases, all your dynamic conditions, and it takes the largest one. It adds about 5%. So if you take 52.294, multiply that by 1.05, you'll see you get roughly 62.3 kilonewtons. So that's why Sidewinder has selected that. Now, if we look at our Takeup tab, so again, this is our output window. If we click on our Takeup, we can see right here the belt line tension, and this is another point I want to make. Sidewinder, in Sidewinder, you always work with the belt line tension. Because the belt line, the counterweight mass can vary from the belt line tension depending on whether we've got a hanging counterweight or we've got a vertical gravity counterweight, whether we've got a 1-to-1 reeving or a 3-to-1 reeving or 1-to-4 reeving, whatever. So the take-up tension is always specified as the belt line tension, and you're also, when you're working in Sidewinder, you're always working with belt tension, so it makes much more sense to specify that as a belt line tension, and then there's also no confusion as to what all the rest of the forces are, because you've got your belt line tension. Well, if you want your pulley tension, it's just double that. If you want your take-up tension, then you've got to calculate it, whether it be a hanging counterweight, like I say, or some cable reeving. And I'm going to actually, let's just go through that right now. If I click on the cable reeving ratio here, 0 to 1, 0 to 0, or if I leave it blank, assumes this a fixed hanging counterweight. In other words, in this case, the pulley displacement and the counterweight displacement are equivalent. In this case, if we take our belt line tension, multiply that by 2, that's got to equal our gravity counterweight mass, or our counterweight mass times gravity, which turns out to be 12.7 or 12,700 kilograms. Okay, so those two numbers match. If we take 12,706, multiply that by 9.81, we get 124,645, which is double our 62,300, basically. So that's where that comes from. Now, if I go over to our cable reeving ratio and I say I make it a 1-to-1 cable, essentially keeps the same counterweight mass. We still got 12.6. In this case, our take-up cable tension is going to be twice that. It's going to be 124 kilonewtons. This is our actual cable tension. And if we look at our displacement, our pulley displacement and our counterweight displacement are the same. If this moves 1 meter, this moves 1 meter. Now, if I went up here and I said, okay, let's make this a 1-to-2 ratio, and I run it, now we can see that, hey, our take-up displacement is now half, because if this moves 1, this now only moves a half. However, our take-up mass has increased. Okay, our cable tension is still the same, but now our take-up mass has increased because we've got two cables essentially here. So again, this is just straight mechanical engineering, but it's very nice because you can go up and select different cable reeving ratios, and Sidewinder automatically shows you what your layout is, what your cable tension is. In fact, it'll even estimate a cable diameter and a sheave diameter for you. It'll show you both your pulley displacement as well as the counterweight or the take-up displacement and the take-up mass. So it becomes a trade-off between, do you want to build a taller that has more displacement and use a lower mass, or do you go with a higher mass take-up with less displacement? And those are financial trade-offs and trade-offs we have to do as engineers here. But Sidewinder pretty much lets you select all the normal commonly used reeving ratios. Again, if I select 0 to 0, it's going to go back with our fixed hanging counterweight. Now, again, I just clicked on the Takeup tab, and this is the all. This is the summary of all of our cases. So with this, we've got, again, our type, gravity, belt line tension, the take-up mass. If we had a cable reeving ratio, let me just put 1:1 again here so you can see it selected, showed you the cable tension, cable diameters. Also shows us what our displacement is. So during steady state running, from all our different load cases and our thermal conditions and whatnot, the take-up travels from negative 1.1 to 1.2 meters. And during momentary conditions, starting and stopping, we actually travel from minus 1.4 to 1.2. The total displacement, including thermal, is going to be 2.6 meters. Permanent elongation is 15.28. Permanent elongation is simply calculated. If you know what your specific belt manufacturer is for the different belts, you can go ahead and enter that right there. By default, Sidewinder will assume a permanent elongation of 0.1% for a steel cable belt and 1.3% for fabric belts. Again, that varies by different manufacturers. If I go up to the help menu here and I go down to belting catalogs, I can just look at some of the different standard catalogs. For example, the Goodyear Plyline Plus here's the average permanent elongation, varies from 0.08 to 1.5. There's a 1.7, so it varies depending on the belt construction and type and number of plies and so on and so forth. But by default, again, Sidewinder will use 1.3 for a fabric belt and 0.1 for a steel cord belt. Splice allowance is essentially the allowance that we give to add a splice in there. For longer belts, it actually allows 2 splice allowances, and if I click on my belting tab here, I can see this is a 2-step belt. Sidewinder's automatically estimated a splice length, including the bias that we need for the belt, of 1.2 meters. And right there's our 1.2. Clearance is essentially, that's actually a function of the conveyor length as well. Longer the conveyor, we leave a little bit more clearance, but that's just extra clearance that you have for pulleys and whatnot, so you're not right at the edge. And then a summary of all of them. So this is quite a nice table here. You can go ahead and break down each individual case as well from empty. Something I want to point out is Sidewinder always assumes that the 0 pulley position is your steady state empty running. So running under empty steady state conditions, that's 0. When we fully loaded the belt, we could see the take-up would be at minus 0.1 meters. In the case of the incline high friction, the running condition would be at minus 1.1. If we had to start the belt in that case, it would actually move from our 0 reference point, which is empty steady state running, to minus 1.4 meters. And there's our decline. So you can flip through each of these cases. We'll talk about this a little bit more in the next tutorial when we talk about different take-up types. But I think that wraps it up for the inputs as well as the outputs. Again, the only input we didn't specify is we certainly could have went in and specified a different take-up. For example, if I went in and said I'm going to put my take-up tension as 40 kilonewtons and I run it, you can see Sidewinder warns you all kinds of things. Hey, you can have some drive slip, you've exceeded the sag criteria, so on and so forth. So it's kind of nice. It points those out right away. In fact, down here it says, hey, you're slipping the motor during starting. Boom, you're at 103% of your tension ratio. So, all right.